So thank you for the kind introduction, and thank you, the organizer, for inviting me and for having me here. It's a pleasure to be here. So today I'm talking about this problem. It's a problem of frequency recovery. So can you hear me? I discovered this problem at the BNP in Oxford. There was a talk by Diana Kai, and she was presenting a joint work with Michael Mitzenmacher and Ryan Adams. And I found it fascinating, so I started working on that, and I think that I have a kind of complete picture at the moment that I can share with you. So it's a kind of problem where it fits into this area where you don't have access to the real data, but you have access to a corrupted version of the data, and the sketch is an example of a corrupted version of the data. Okay, so one slide to describe the data, describe this kind of corruption, and state the problem. So I consider a collection of M observations. So each xi belongs to an alphabet of symbol. M here is typically very large, and S is an arbitrary alphabet. So I have a collection of M symbols. And so as I said, I don't have access to this observation, but I have access only to a lossy compressed version. I will clarify this in a bit, or sketch of the data. So what means? It means that I pass my data through this random function, which is an hashing function, and I map each data point into this space, and W is something that I select. And so basically what I'm doing, I construct these CJ that are called buckets. So for each J, what I'm doing, I'm counting the number of observations that are mapped into a particular bucket. Okay, so I'm collecting, so two different symbols could have a collision, and they could go into the same bucket. And Cj is the empirical frequency of this bucket, and this is what I observe for J from 1 to W. And the goal is the following. So based on this sketch that is observed, what I want to estimate or recover is the empirical frequency of x n plus 1. So a new observation arrived, and I want to estimate or recover its empirical frequency. Of course, it's trivial if I could observe the x. I have just to count, but here I don't observe the x. I observe this compressed version of the x. This is what I call frequency recovery. There are many other recovery problems, but in principle, if one can solve this one, can easily move to other problems, and I will discuss later on this point. Okay, so motivation for using sketching. So why that? There is a very nice book by Cormod and his small summaries for big data, and it's a book on computer science. But I think that there are many useful stats inside, and the motivation for using sketches have changed along the time. Why that? Because of technologies. So Peter yesterday gave a talk on that. So we need somehow to adapt to the technology. And some motivation are here, so along the time. So it started with memory constraints problem. Okay, so I didn't have enough capability in the memory to store my data. Then massive data streams, so large amount of data, not only large amount of data, but they arrive at a high velocity. Okay, so I need to deal with this kind of data. Web scale application, I mean, I don't only need to store this huge data, but I also need to have access to this data quickly. So when I search something on Google, I don't want to wait minutes to have an answer. So fast queries. Okay, so here in marketing for online advertising, big data analytics, when we want to do statistics on this huge data. And then most recently, private data analysis and fairness. I mean, these sketches, as you can see, it's a kind of aggregation. So aggregation creates privacy, protect privacy, and there is a debate on what do if aggregate data or perturb with a little bit of noise, and I will discuss later on this point. And finally, I will also discuss this optimization in machine learning, so dimensionality reduction and fast linear algebra. So these are all potential applications of sketching and many other. Okay, so I will start from scratch. So model-free frequency recovery. So suppose that I don't any modeling assumption on the data. So these X are just numbers. No modeling assumption, not even any form of symmetries for my data. And the question is what I can do if I don't assume anything on the data. Okay, I can do something. The best thing that I can do is to look where the xn plus 1 is mapped to the hash. And I use this count as an estimate of my frequency. So it's, of course, it's an overestimate, but it's the best probably that I can do if I don't assume anything. And the count mean sketch started exactly from this trivial estimate. So how can I improve that? The count mean sketch is probably the most popular algorithm to solve this problem. And the idea is to use more hash function. Okay, so, and the idea is it's nowadays called multi-view learning, but in a different perspective with respect to what Maria discussed yesterday, and I will show you in a bit. So I consider a collection of random hash function. I have D random hash function. And with this property, it's called universal hashing. So it's typically a property that it's difficult to achieve, but an approximation in some sense of this property is fine. And I will show an example later on. And what I do is the following. So every item is passed through the hash function, and I'm going to increase by 1 the counts of the bucket where the observation is mapped. Okay, and I do, and these hash functions are independent of the axis, and I construct my hash table. Here we have an example with the 4 hash functions. So I proceed in this way. I map all my items through this hash function, and I construct this hash table. Okay. So randomness enter into this game through the hash function, and the count mean sketch proposed the following estimates. So I take the minimum of the counts of the buckets where the individual is mapped. It makes sense because it's an overestimate, so I'm going to take the smallest one. Okay? And there is a kind of guarantees for this, a confidence interval. It's a very simple, so it's constructed by using the randomness of the hash function and by simple Chebyshev inequality. Okay, there is something more sophisticated in terms of Chernoff bounding, but we cannot go far away because here I'm exploiting only the randomness of hash function. Data are fixed, no model, no symmetries, nothing. Okay, so this is what it is used. So the count mean sketch is the most popular algorithm to solve this problem, and it's model-free, completely model-free. And now I start with my contribution. So the first part is the following. So what about, so people start thinking about what about if I do some statistics on this problem? What about if I place a model on my X and try to solve the problem under some modeling assumption? And I will start with the non-parametric framework. So for the moment, no prior. And I try to see the limits of doing this, of solving this task. Limits, I mean, what are the boundaries? So what I can do, what I cannot do, what I should do, but without taking a prior. So this is, this terminology has been coined recently. So learning augmented means that I assume a model for my data. And here some references. And typically approaches are parametric, so I fix a distribution. Bayesian non-parametric, some resampling techniques, I mean bootstrap, and recently it's quite popular conformal prediction, which is conformal prediction is something that is very close to the count mean sketch because I'm assuming just a form of symmetry on my observation, no modeling assumption, and we can get confidence interval non-asymptotic with the valid coverage. Okay, so let's place a model. The most natural model is the following. I have symbols. So I assume that x1, xm is a random sample from P. P is a discrete distribution, is on space S, and it's an unknown discrete distribution. Then I have an hash function, random hash function. It's independent of P, so independent of the X, and then I pass everything through the hash function. And I construct my sketch. Okay, so what is the goal? The goal is can we recover my frequency under this modeling assumption. Okay, so now here I have a model, so I can compute some probabilities. Okay, and for instance, we can compute this probability. So it's the conditional probability that f is equal to r, given the sketch, and also given this information, which is basically something that I observe. So I have the information about where xm plus 1 is hashed. Okay, so I know that. And h, in this talk, h will be fixed because it's independent of p. So I can use somehow the freezing lemma and consider that fixed for the moment. And then if I'm able to compute something like that, I can take the expected value and start from this point. Okay, so the goal is to compute these probabilities, and that's my first result. And so we can compute the probabilities, and something strange appears. So I mean, the model is on p. P is my unknown quantity, but if you can see, this quantity is a discrete functional, but not of p, but of what I call pj. What is pj? Is the probability distribution that control the frequencies, the configuration into the specific bucket where the next one is mapped. Okay, so I have a model on P, but I have a discrete functional on Pj, which is quite unusual. I mean, if this was a discrete functional on P, we know how to do that, but that's different. Okay, and here's some notation. I define Pj, the masses of this conditional distribution, and then I can take the expected value, and I obtain something like that, which I call the oracle estimate. If I know P, that's the right quantity. I mean, and if you see, it's quite meaningful for who is familiar with the index of diversity. What is that? I'm taking the empirical frequency of the bucket, and I'm weighting that empirical frequency with this coefficient. But what is this coefficient? It's the Simpson index of diversity of the bucket specific. Okay, I repeat, if this was a functional of the P, it was fine. But it's a function of Pj. So I don't know what to do. And so, okay, this slide, I will go very quickly just to explain that that's a difficult problem. Because in general, if I have a problem like that on a discrete function on the P, I can observe something like this equality. So I can observe that the masses can be written as the expected value of the number of distinct symbols with frequency r in the bucket. And then the typical approach, non-parametric approach to construct the estimator for this object is to replace this expected value with the empirical quantity. But we don't have the empirical quantity because the only information that we have with the bucket is how many individuals are into the bucket. We don't have any information about the configuration. We cannot observe that. So we cannot construct non-parametric estimator in the classical way, so like in way of Robbins, non-parametric empirical base. And so somehow I like to see this problem as a statistical problem where I have only information on the sample size. It's like estimating something when you know only the sample size, which is a kind of strange. Okay, so this oracle estimator suggests that we could focus on a linear estimator. So you have Gj multiplied by a quantity. So we can consider a class of estimate of this form, some beta multiplied by the empirical frequency of the bucket. And then I try to do some study on that. I consider this risk, and I try to identify what is the worst case optimal estimator. So under this risk, and how can I do that? I upper bound this risk, and then I minimize with respect to beta. And that's the result. It's an informal statement. So it's informal because I'm not placing all the assumption of P. And so if roughly, if the support of P is large enough, it can be proved that the upper bound is tight, and this upper bound is achieved by the degenerate distribution P star. And this upper bound is minimized with respect to B when beta when beta is equal to 1. What means that? It means that I recover the trivial estimates. Okay, so this has two meanings. One, it's a rigorous proof of the trivial estimate. So it's saying that the trivial estimate is the worst case optimal estimate. And the other thing is that the other message that if we don't place assumption on P, we don't go far away. Okay, so that's my motivation. So and the most natural approach is to try to place a prior on P, and that's what has been done by Diana, Kai, and Kotos, and in these other papers, and also some parametric stuff has been done. If I do that, I can compute my posterior mean, and the posterior mean is as the following form, and it's complicated. I mean, it's complicated because I have to integrate out P, and but there is the sketch around. So it's doing this. It's quite complicated. In this paper, one of the main messages that it's very complicated, this object, and one result that is useful to tell you that maybe it's better to move a bit away from the standard Bayesian procedure is the following: that the posterior mean is of this form, so linear in C, if and only if P is a Dirichlet process. So it means that I can get something in this class of linear estimates, which are quite simple, if and only if the prior that I assume is the Dirichlet process. If I don't do that, if I take any other prior, consider, for instance, the class that we know of normalized random measure, this expression will depend on all the frequencies of the buckets, and it's become really, really untractable. So it cannot be computed. So you have a kind of nested summation. It's complicated. Okay, so this result somehow says, okay, from one side, I want to place assumption on my P, and I like to place assumption on the P, and we know many priors that could fit into this framework, heavy tails, exponential tails, and things like that. But this result says that only if you assume the Dirichlet process, you get something linear in Cj, which is something that I want. Okay, so from one side, I want some flexibility in placing the prior. From the other side, this result say that you can pick only the Dirichlet process. Okay, so we need to find solutions because especially in this problem, when you deal with large alphabet having power law behavior, it's quite common. So we know that the Dirichlet process has not this problem. Okay, and that's the approach that we propose to solve this task. And so it's what we call smoothed Bayes. It's not a terminology that we invented, and it's something that we took from an old paper by I.J. Good in Biometrica. And the idea is the following. So it's very simple. So instead of using the prior, I shouldn't say prior, to compute the posterior through the Bayes formula, we use the prior to smooth this oracle. So we take an expectation with respect to the oracle, and in this way, we include information on the P. Okay, and that's something that has been done by Good in this paper. I know this paper, that's why I'm referring to this paper. I think that there could be other works that consider the same approach. So it's still a complicated problem. Why? Because I'm taking an expectation with respect to P, but this functional is not with respect to P. It's a discrete functional with respect to the P, J, that is induced by the hashing. So still I have, it's not, in the paper of Good, the problem was to compute this expectation of discrete functional with respect to P. So here it's different. So I need to be more careful in solving this. Okay, so here is what I said. Basically, I need to, if I want to solve this task, I need to find a distribution for P such that I'm able to find the distribution induced by the random hashing. Okay, so that's the main, because if I'm able to do that, I can solve this expectation. And then also I would like to, that the potential hyperparameter that I introduce on P can be estimated somehow using the sketch. because here everything is shifted to the sketch. That's the only information that I have. And okay, so that's the tool that I'm going to use. It has been useful in this context. It's a completely random measure. So we know now it's Thursday. We know everything on completely random measure. So I assume I consider it's a Poisson random measure. It's important that it's homogeneous. So I mean the intensity can be factorized into something that controls the distribution of the jumps and something that controls the location, and G0, which must be non-atomic, and theta is a parameter. It's a positive parameter. And then under certain assumption on this intensity, that guarantees that the total mass of this random measure is finite, almost surely, I can do this operation. So basically, I take my completely random measure and I normalize by the total mass under certain assumption on the intensity, which guarantees that T is finite almost surely. And why these are useful? Because they have this nice property that I call the restriction property, but it's very, we all know these things. So if I take a normalized random measure and I consider a set A, and I denote by PA the corresponding random probability measure that is restricted to that space. So that's the notation. So what I have is that the restricted random measure, completely random measure to that set is still a normalized random measure. I just need to adjust the parameter theta with respect to what? To the mass of the probability G0 in the set A. And then I have to adjust this, renormalize this probability. But the important thing is that rho is the same. Okay, so somehow if I'm going to restrict to a certain subset, I still have the same normalized random measure. So that's the point. And if I combine this with the fact that the hash function is independent of P, and that's the part where it's important, the independence, and under the property of strong universality that I stated before, I have that if P is a normalized random measure with some intensity, Pj is again a normalized random measure where I only need to rescale the parameter theta by what? By the number of buckets that I fixed, because strong universality guarantees uniformity on which these elements goes into the buckets. Okay, and so I have done, because I know how to compute the expectation, and that's the result. So if I have a random sample from P, and P is a normalized random measure, homogeneous, then I can compute the probability masses Pj of my conditional distribution, and it's what? Just a mixture of binomial. Okay, so it's a mixture of binomial, and the parameter Cj is the size of the bucket, R is the point where I compute the mass, and it's mixed with respect to this density Fvj, which has this form. I have examples, specific examples. That's a general result, but I will show you examples in a bit. So the main message is that the distribution, that the conditional distribution that I presented before is just a mixture of binomial, which is very, very simple. I want to compute my expectation. We know how to do that, and it's the following. So it's Cj multiplied by the expected value of this random variable Vj. So it's something linear in Cj, which is what I want. I put assumption on P. Okay, I didn't compute the posterior, but we will see the link in a bit. But I get this estimate, which is very simple. Okay, so this estimate is non-Bayesian. I mean, because I'm not computing any posterior expectation. So let me try to see if under a Bayesian model, what is this estimate? Okay, so if I assume a Bayesian model, what is this estimate? Okay, and I have this result that says that the estimate that I consider this epsilon f, which is this one, under this square loss, if I optimize with respect to all the possible estimates that are linear in CJ, the one that I obtain is the best one. So let's say that these estimates, it's obtained in this strange way that I call smoothing, but it has a Bayesian meaning. It's the best linear Bayes estimate that I can obtain, and it's also unbiased. Okay, so this should say that, okay, this smoothing is not very weird. I mean, so I'm doing something that has a meaning. So it's the best that I can do in a Bayesian sense if I restrict to linear estimates. And okay, so these are some comments that yes, that I can see. So this is, I call it Bayesian validation because somehow I'm taking an estimator and I'm staying to a Bayesian framework and I'm providing some result. Okay, some examples of this. That's very general for normalized random measures. So let's see some specific examples. So the first one is the Dirichlet process. We know that the Dirichlet process is a normalized random measure when I specify this particular intensity. And what I'm interested in, I want to focus that the Dirichlet process, we know that it has exponential tail. Okay, so it's a full support, but that we have this property of exponential tail behavior. And this is an application of the theorem that I presented before. So basically, if I call it DP smoothing, so if I take a random sample and assume P a Dirichlet process, I have my sketch. So this random variable that was mixing the binomial is just a beta. And my estimate is CJ, so the frequency of the bucket multiplied by this quantity. Super simple. So somehow I'm weighting the frequency of the bucket by this quantity. And then, of course, I will have to learn this theta. Okay, but I will postpone a bit. Okay, so, and this estimate that I obtain is coherent with respect to the worst case analysis, because if theta goes to 0, the Dirichlet becomes degenerate in a point, and then what means? It means that I recover the trivial estimates. Okay, so that's coherent with the worst case analysis. And then the other nice thing is the following. So the estimates that I obtain coincide with the posterior mean estimates. Okay, so the one obtained by Diana Kai and re-obtained in another work with Emanuele Dolera and Stefano Pelluchetti. So they coincide. So the posterior mean estimates coincide with the smoothing estimates. So now the question, is the Dirichlet process a special case for which this is the only one for which this happens? Yes. Okay, so the Dirichlet process, so if I denote by the posterior mean, the smoothed estimates with respect to normalized random measure, and here the posterior mean estimates with respect to normalized random measure, they coincide if and only if P is the Dirichlet process. So this is quite interesting because it means that if I don't do this smoothing and I want to move away from the Dirichlet process, I mean, I'm kind of stuck if I do the posterior estimate. Okay, another example is the normalized generalized gamma process. So here I cannot use pit manure because it's not a normalized random measure. I need just normalization without any change of measure. So it's a normalized random measure with this intensity. And what's the remark is that it has a power law tail behavior, and the tail behavior is controlled by alpha. Alpha controls the tail behavior. When alpha goes to 0, I'm going through an exponential tail behavior. When alpha goes to 1, I have a very extreme heavy tails. And the proposition, again, is the following. It's an application of the main result. Again, my estimate is CJ multiplied by a coefficient that I can easily compute. It's very simple. Okay, so another example of linear, but now I'm in the power law tail behavior. And okay, and just one comment about estimation of hyperparameter. In the Dirichlet case, it's very simple because we can resort to finite dimensional distribution. And so basically, we can estimate theta, I mean, by I mean, by maximizing the marginal likelihood, or otherwise we can put a prior, but we have access to the likelihood of the sketch. So it's quite easy. It's a Dirichlet multinomial likelihood, so it's simple. And otherwise, it's not simple. If you move away from the Dirichlet process, it's not simple. But we can do something that I used with in some works on conformal prediction. So here M is very large. So we can maybe take a little bit of data without sketching them and using that to estimate the parameter. Alternatively, we can do some kind of simulation-based approach, create a synthetic sketch data set and try to optimize the data by some, I don't know, minimizing some distances between the observed and the synthetic. We can do something that, but if we go away from the Dirichlet process, it's not simple. Okay, an example. So here I consider synthetic data generated from the pit manure process and from a zip. Why I want to do that? Because I want to stay in the heavy tails regime, and I want to see if I apply the Dirichlet process in the heavy tails regime, does it make a difference with respect to the normalized? And it does. So here I'm using the arithmetic hashing, which is the standard one. So I mean, it's basically, so the idea is that I take P, which is the prime number larger than the largest observation that I have, and A and B are random quantities uniform between 1 and P minus 1. So that's the idea. And these are the results. And you see that in the blue line, so this is a quite extreme heavy tail behavior because it's 0.75. And here it's C is the parameter of the zip. When C is small, you have heavy tails. Okay. And it seems that using the normalized generalized gamma process makes a difference in terms of this mean error that we considered. So this was just to motivate that working with the generalized gamma process makes a difference. Okay, okay, some concluding remarks. So I have time. Yes, okay, so and some direction. So we consider this problem. So what I didn't present, and I said at the beginning, is that if we are able to solve this frequency recovery problem, we can easily move to other problems. And one important problem is the cardinality recovery. So I mean, I observe the sketch and I want to estimate or recover how many distinct symbols there are in the sketch. And the classical algorithm in computer science is the hyperlog-log by Philippe Flageolet, and it's the standard, it's a benchmark algorithm. And with our approach, we can also do this, we can apply this smoothed Bayes also to recover the cardinality, which is an important problem. We can consider multiple hashing in the style of the count me sketches. So, and using this multi-view learning approach, it's all in the paper. About uncertainty quantification, the smoothed Bayes approach is not good. So we need to resort to other things on conformal prediction. Somehow you can conformalize credible intervals, and also this stuff is in the paper empirically, and it's developed in this work with Matteo Sesi and Edgar Dobriman. And okay, applications, I didn't talk about much. I didn't talk about that, but it's there is a huge number of applications in the paper, and it works well. I want to say that it's not surprising that it works better than the count me sketch because we have more assumptions here. So we are smoothing more. And some directions, so that I really wanted to say something about that. So what I presented is in a static or batch. I mean, I didn't do anything online, and the count me sketch is typically to do online stuff. And here I think that I added this because during this conference, I learned a lot about post-based learning, and I think that that's the right direction. I think that if you want to solve these problems online, probably the best thing to do is to go through that kind of approaches. We can consider more general discrete data, so move away from species, so I mean symbols, but we can consider features or feature with some intensity, so traits and things like that. Privacy and fairness. Okay, so sketches are used both to privacy and fairness. Why? Because they aggregate observations. So you can preserve some form of privacy, maybe not differential privacy, but there are forms of privacy preserved by sketches. And here there is, I think, a huge debate between aggregating to create, to satisfy privacy, or perturbing by adding a little bit of noise. And other two things that I believe that are interesting to explore is, so what I presented in the context of multiple hashing is nothing more than a special case of compressive sensing. Okay, because the sensing matrix is basically introduced by using the hash function, and I apply this binary matrix to my data, and I obtain the sketch. So what we are solving here is a discrete example of compressive sensing, where the sensing matrix is constructed to the hash function. And then other things, so this is explained in this nice paper by Gilbert and Indyk. And also very recently, they apply sketches in a different direction. So here I apply sketches to compress my observation, but sketches can be applied also in the direction of dimensionality reduction. Okay, so you can apply this machinery of sketching to reduce dimensionality as per the Johnson-Lindenstraut theorem. In that case, the matrix is dense. So in this case, we can use sparse matrices. And there is a very nice work, non-Bayesian, by Griboval, Blanchard, and Cotter, which is compressive learning, and they use sketches to reduce the dimensionality. It's completely non-Bayesian, and I think that they're promising to do some work in the Bayesian in that direction. And I stop here. Thank you for your attention.
Thank you for the very interesting talk. We have time for questions. Just to start us up, so in the example that you gave, the numerical example for invariant, I wonder, can this be applicable to multivariate hashing? Like you cover the covariance structure?
The covariance structure?
Yeah, I think I'm drawing
I don't know. The multivariate case is applied in the framework of multi-view learning, or you can also use product of experts and things like that, because you have to aggregate these different hashing structure, and you have provided an estimate. So, but I don't know about covariance.
Oh, please.
So some people use hashing in estimation. So you do the hashing and then it's a model on your recovered values. Is that a problem that you thought about? That's kind of a natural Bayesian thing to propagate the uncertainty from recovery into the estimation.
No, I didn't think about. I actually don't know this, but we can chat about that. So I don't know this problem. No.
The uniqueness for the Dirichlet process, some of those that driven by the Dirichlet process, in the sense being tied to the empirical speed.
Yes, because it's one of those properties, those uniqueness property. Like I think that what plays a real role is the predictive structure. So if you look, it basically depends in the probability of discovering new things. It depends only on n, on the sample size. And also the other thing that you have access to, it's a very special structure. I think that this uniqueness result is probably a consequence of all these uniqueness properties of the Dirichlet process. You don't actually, in the Dirichlet process, in the empirical part of the predictive, it's a true empirical distribution. In the Pitt-Magnol or other things, it's not an empirical distribution. It's an empirical distribution plus the number of these things that you observe. So it's it's a strange empirical object.
More questions? Well, if not, let's thanks Stefano.